So can you hear me?
Yes, sir.
Okay, okay. Okay, I have uploaded some exam type questions. Okay, so try to do them. Okay, so I will just give you a very brief recap how to do it. Okay. Uh, okay. So you can see that there are some matching problems. Okay. This type of matching problems. I hope that we have done already some matching problems. Okay. So try to do these questions by yourself, and also the answers are also given. Okay. So I think you can understand them by yourself. Okay. So that is not a complex one. Okay. Uh, and so the matching question will come. Okay. Definitely matching question will comes. Okay. So you have to thoroughly study the matching techniques. Okay. Especially uh, this 1 to 4 balloons matching techniques, and balance matching techniques, and maybe wait a minute, and lambda by 4 coaxial balloons. Okay, so balance. Okay, so there are some kind of balance. Okay, so you need to study those balance, especially 1 to 4 balance and lambda by 4 balance. Okay, so study them carefully, and I think we have discussed the resonance of uh, uh, antenna. Okay, the resonance means the antenna impedance should be pure resistive. Okay, so that means the reactance part should be cancelled out. Okay, most probably antenna has inductive reactance. Okay, so if you put capacitive reactance, yeah, okay, okay, definitely I will give. Okay, so if you put a series capacitor uh, with respect to the uh, with the antenna. Okay, uh, and the inductive reactance and capacitive reactance are equal, then antenna will become uh, resonant, self-resonant. Okay, so study the self-resonant also. Okay, that means inductive reactance should be equal to the capacitive reactance, that is resonant. Okay, very simple. Okay, so I hope you can study them by yourself. Okay, and so this kind of question also will come. Okay, so this is from LO1. Okay, so most probably you will given uh, this kind of intensity function. Okay, then maybe you are asked to find the directivity or the directivity function. Okay, so if I just recap you quickly. Okay. Okay, maybe you can remember that uh, we have learned about the antenna um, propagations. Okay, so first to find the field of the antenna, first maybe you can remember that we have find the magnetic vector potential. This is we call magnetic vector potential. Then using this magnetic vector potential, we can derive the H field at E field of the antenna. Okay. Then using this H field and E field, uh, we have defined one parameter that is called, maybe you can remember this, average power density. average power density. Don't worry, these things will not come to derive, okay? So don't worry, okay? So average power density is there, okay? So this means the power across unit area, okay? Power across unit area, okay? Then you have to, then we have found the total radiated power, okay? Total radiating power, okay? So this is average, that is the power for a unit area, okay? So if you have done the, if we do the surface integral with this S average, we have to get the magnitude of S average, okay? And if we do the surface integral over the surface, okay, we can find the total power radiated, total radiating power, okay? And so we are most probably we are using spherical coordinates, okay? So this one can be used, this one can be written using spherical coordinate like this, as I can remember. D theta d phi, we have learned these things, okay? So most probably this integration will be from 0 to 2, 5 and 0 to 5, okay? And these things are there, okay? And d theta d phi, okay? So most probably you have to do this integration if you want to find the total radiated power, okay? And then maybe you can remember that we have found the radiation intensity. That is important, okay? Radiation intensity, okay? So radiation intensity is given, most probably it is a function of theta and phi, okay? It is a function of theta and phi, okay? Radiation intensity means, maybe you can remember that it is a power per unit angle, power per unit solid angle, okay? So we can find it using the average power density. I think we have defined these things, okay? So if you get R square S AVG, average power density magnitude, we can get the radiation intensity, okay? So this is normally important, okay? So maybe you have to use this equation, okay? So you can see that the U is given in that question, okay? In the second question, radiation intensity is given, okay? And this is the definition for the radiation intensity, okay? And you are asked to find the directivity, okay? So directivity function means the theta phi. It is also a function of theta and phi, okay? And it is given as, maybe you can remember that, intensity, radiation intensity is divided by U naught. This U naught means the intensity of isotropic antenna, with same power, with the same power, okay? So these things we have discussed, okay? So this is how we find the directivity, okay? Now you can see that, okay? So if you are asked, if you are given this radiation intensity, and if you are asked to find the, this directivity function, you need to have a relationship between these two, okay? So you can see that, okay, there is a relationship, okay? So you are given this one, then you have to find this one, okay? So maybe this U naught, okay, U naught is defined as total radiated power, okay? Total radiated power divided by 4 5, okay? So you can find theta 5 pt 45. Okay, sorry, directivity function is equal to u theta 5 u naught is equal to pt divided by 45. Okay, so this is the intensity with the same power of isotopic antenna. Okay, isotopic antenna is radiating uniformly in every direction. So that is why we have to divide the total power by 4, 5, because the isotopic antenna is radiating uniformly. Okay, so directivity function you can define like this. Okay, so in the second question you have to use this identity actually for the second question. Okay, so you can see that the intensity is given. Intensity is given, you are asked to find the directivity function. Intensity is given, you are asked to find the directivity function. Okay, so here you have to calculate the total radiating power. Okay, so you have to calculate in the total radiating power. For that one, so the total radiating power you have to find. Okay, you have to find using this. So somehow you have to find the total. Yeah, so the directivity, you have to use the Umax, okay? The maximum radiation intensity. So we are talking about directivity function, okay? We are talking about directivity function. The second question, you are asked to find the directivity function, okay? So if you are given to find the directivity, you have to find the maximum intensity, okay? The maximum intensity is divided by this value, PT 545, you can get the directivity, okay? So if you want to get the directivity, D, that is Umax divided by PT 45. This is directivity, okay? This is directivity. For the directivity, you have to get the maximum radiation intensity, but to find the directivity function, you have to get the radiation intensity. Okay, so here you have to get the maximum radiation intensity. Okay, I hope you got it. Okay, now anyway, you need to find this total radiating power. You need to find this total radiating power to find the directivity function. Okay, so then how to find that? Okay, actually that part maybe I haven't done. Okay, so these equations are given. Okay, these equations I have given. Okay, so the total radiating power. Okay, so you can see that radiation intensity is a power per unit angle. Okay, so this is this one. Average power density is a power across unit area. Okay, so the total radiating power you can find by do the integration. Okay, integration by doing the surface integration of this S average, okay, average power density, because it is a power across unit area. Okay, now what is this U? What is this U? That is the power per unit angle, unit solid angle, power across the unit solid angle. Okay, so if you do your integration, okay, if you do your integration, okay, that U integration, okay, over the angle, over the solid angle, okay, you can find the total radiating power, okay, total radiating power, okay. So this integration, okay, this integration also have to do in theta and phi direction. Okay, so if this is sphere, okay, so if this is if this angle is considered as d omega, okay, the very tiny solid angle, okay, so you are doing this integration within this angle, okay, within this angle, okay, so you have to do this integration from here to here and also from here to here. That means in theta, with respect to theta and with respect to phi, okay. So uh, phi, okay, so if you are doing the total uh, integration, okay, so this theta and phi may be given, okay, this theta and phi may be given. For example, here is that given. Here theta and phi are not uh, defined, but 2.2 part, this parts, in this part, you can see that the theta is given. The theta, the the area, what is this called? The limit for the theta and phi are given, okay? So you have to do the integration within this limit, okay? Within these limits, you have to do the integration. Theta between 0 and 5, phi between 0 and 2, 5, okay? So here also, you have to do this integration, okay, with respect to theta, okay? And when you are write it uh, with respect to um, this d omega in the terms of a spherical coordinate, you will have here sine theta, d theta, d phi, okay? So you have to do the integration with respect to d theta and d phi, okay? So this phi angle most probably will be 0 to 5, okay? And this theta angle also may be 0 to 5, okay? So if you are given the range, you have to use that range, okay? You have to use that limit when you are doing the integration, okay? Then you can put this unit uh, radiation intensity, okay? So you have to do this integration to find the total radiated power, okay? So if we check this one, okay, so this is the 2.1, okay, this is the 2.1, okay, this 2.1, you are given the radiation intensity and you are asked to find the directivity function, okay, directivity function. Then you have to find the total radiating power PT. To find the total radiating power, you have to integrate this intensity function with respect to theta and phi with the limit, okay, using this identity, okay. So you can find the total radiating power, okay. So U is given, then you have found the total radiating power, then using this two parameters, you can find the directivity function, okay. So that is clear, I think, okay. Now, one problem is there because you can see that this this intensity power is very complex one, okay. So if we are going to do the integration, it will be very hard, okay. Actually, sometimes this kind of integration we can't do, okay. So, but for the second part, that intensity function is somewhat simple, okay. So here you can do the integration very well, very easily. So cos 6 theta sine square theta, okay. So first you have to do the integration with respect to phi, d phi. Then you have to consider only sine square phi. So you can integrate sine square phi using d phi, okay, very easily, okay. Then cos 6 theta with respect to d theta, you can find, okay, very easily, okay. So when you do the integration with respect to theta, the phi should be a constant, when you are doing the integration with respect to 5, theta should be a constant. Okay, so here this one you can easily integrate. Okay, this part you can easily integrate. This kind of function you can easily integrate, and you can follow this method. Okay, you can follow this method. Okay, but for this type of question, maybe it is not proper to follow that method, because this u is somewhat complex, and also the limit of theta and phi are not defined. Okay, but you can assume that only theta is there, so most probably theta will be 0 to 5. Okay, so you can do this integration 0 to 5 with respect to d theta, and you can find the total radiated power, but it will be very complex one. Okay, it will be very complex. Okay, so we have to find another method. Okay, so we will try to find, I'm sorry. Okay, I'm talking about this question. Okay, I'm talking about this question. Okay, because I can't see my screen very well. Okay, yeah, I'm talking about this question. Okay, this one, this is the 19th question. Okay, and this question I just talked about. Okay, so you are given this u and you are asked to find the directivity function. Okay, so to find the directivity function, you need to find the total radiating power. Okay, so the total radiating power you can find by doing this integration. Okay, okay, so the u is given, and you can perform this integration, and you can find the total radiative power. Then directivity function you can find using this identity. The u is given, and you have found this total radiating power using the radiation intensity itself. Then you can find the directivity function. Okay, but you can see that. Okay, so that method is proper for this question, for this part. Okay, for this part, that question is proper. That method is proper. Okay, because this is cos 6 theta, cos to the power 6 theta, sine to the power sine square 5. Okay, and theta and 5 limits are also given. Okay, so you can do this integration very 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 easily. Okay, so instead of this you have to apply this given function cos 6 theta sine square 5. Okay, and here sine theta d5. Okay, so first you have to do the integration with d5. Okay, that means this theta functions are this theta functions are is called constant. Okay, and you have to only do this integration. Okay, so that is you can do. Okay, so when you are doing the integration with respect to d theta, so you have to do the integration cos 6 theta sine theta d theta, this integration. Okay, so this integration also you can easily do. Okay, so this integration will not be hard. Okay, you can do it quickly. Okay, so for this kind of questions, okay, for this kind of question, this approach is proper. Okay, this approach is proper. Okay, but you can see that. Okay, but you can see that here. Okay, here the u is somewhat complex. Okay, so when you are going to do this integration, okay, so this integration will be very hard. So you have to find another method to find the total radiating power. Okay, actually another method is there. Okay, another method is there. Okay, I just explain it. Okay, this question will be come to you. This type of question will be come to exam. Okay, so try to study them. Okay, So actually, we can draw the circuits, antenna equivalent circuits. Okay, the circuit, the equivalent circuit for the antenna. Okay, so it is like this actually. Okay, it is like this. Okay, the antenna is actually look like this. Okay, this is we called radiation resistance. This is loss resistance. Okay, and this is complex resistance. Okay, that is also radiated. Okay, so you can feed this antenna by a signal generator source. Okay, and source also will have a specific impedance. Okay, so this is the equivalent circuit for the antenna. Okay, this is the equivalent circuit for the antenna. Okay, for the antenna, actually this is for the transmission antenna. Okay, for the receiving antenna, this arrangement is somewhat different. Okay, for the transmission antenna, this is the equivalent circuits. Okay, so this radiation resistance actually, when you are giving a power, okay, let's say that I using this signal generator, you are feeding a current to this circuit, okay, to the antenna, okay, and some part is radiating, okay, that radiating power, the total radiating power PT is dissipating to this radiation resistance, okay. So you can write this PT is equal to half I square R radiation, okay. This is the total radiating power PT, okay. So that is this one, PT, okay. So if you can find the radiation resistance, or if it is given, okay, you can find the total radiating power, okay. And also complex power you can define as half I square. Okay, this is we called feed current. Okay, this is we called feed current, feed point current. Okay, feed point current. Okay, so that is R radiated plus J X radiated. Okay, so this is the complex radiating power. Okay, this equation we no need to apply. Okay, but you have to apply this equation. Okay, so you have to find this radiation resistance. Okay, so normally antenna resistance is normally referred as R radiation plus this loss resistance RA. Okay, so all the power delivered to the antenna will not transmit. Okay, so only transmitting, the effectively transmitting power is through this R radiation, and some power will be losses. Okay, so that loss is assumed to be through this loss resistance RA. Okay, so the total resistance is R radiation, the radiative resistance plus the loss resistance. Okay, so this is the antenna resistance. Okay, so antenna input impedance is normally referred as RA plus J X range. Okay, so this is the input resistance of the antenna. Okay, so here you can see that you are given the input resistance. Okay, so using this input resistance, you can find the total radiating power. Then you can find the directivity function. Okay, so that method you have to apply for this questions. Okay, for this part. Okay, so this kind of question also will come. Then you have to find the total radiating power using the radiation resistance of the antenna. Okay, if this type of question is given, you have to find the total radiating power doing the integration, by doing the integration. Okay, so that is it. Okay, so one question will be based on these two techniques. Okay, I hope you can do it now very well. Okay, okay, now you will get some question part, okay? Question part from this one, Friis equation, using this Friis equation, okay? So maybe you no need to go all through this note, okay? All through this, okay? So you can, actually there are many losses. As I told you, there are many losses in antenna, okay? One losses is the due to the loss resistance, okay? That is one loss, okay? And there are other losses, polarization loss and insertion loss, that kind of losses are there, okay? And this Friis equation we normally use to find the received power, okay? If the power is transmitting by antenna, okay? Okay, let's say that you have antenna, okay? Antenna here, okay? So that is the transmission antenna, okay? And the distance is R, okay? And there is a receiving antenna, okay? And this transmitted power normally referred as P in, okay? This one. The received power is PR, okay? So you can find the received power using this equation, okay? And this lambda is the frequency, okay? So if the frequency is given using V equal F lambda, you can find this lambda, okay? This R is the distance between the two antenna, okay? Two antenna. And this is ECD, okay? This is we call the antenna efficiency, okay? This is we called antenna efficiency. But we haven't discussed about the antenna efficiency, okay? There is another parameters called effective warpage, okay? We haven't discussed then, okay? So this antenna efficiency is mainly depend on that effective warpage, okay? So no need to worry about these terms, okay? So if this is not given, you can assume as it 1, okay? This antenna efficiency as 1, okay? And these are the gains, okay? Antenna gains also, I think we have defined what is gain, okay? So these are the gains of the antenna, okay? So this is the gain of the transmitting antenna, and this is the gain of the receiving antenna, okay? So most probably you will be given these gains in dBO without value, okay? Then if you are given this maybe using this equation, most probably you will ask to find this received power, okay? So or maybe the received power may be given, you are asking that you should have a minimum receiving power for the operation, for the proper operation. The Rx should have this minimum receiving power, okay? So this receiving power is given, maybe you are asked to find this minimum transmitting power, okay? So that kind of question will come using this equation. So you have to directly apply the values to the equation, then you can find any unknown parameter, okay? So that is very easy, okay? And once we actually this is the complete Friis equation, okay? So all type of losses are including here, okay? So these are depend on insertion losses. These are depend on insertion losses, okay? And this terms is depend on, actually that is called polarization factor, okay? So that is depend on the polarization polarization loss, okay? So these things are not in your syllabus, okay? That is why I haven't done these things, okay? So polarization is not in your syllabus, okay? So normally uh, you will be given properly polarized antenna, okay? So the antenna, so for example, polarization means the orientation of the electric field, okay? So If the electric field is vertical, we call it vertical polarization antenna. Okay. So if there is a transmit, if we have a vertical polarization transmitting antenna, we should have a vertical polarization receiving antenna also. Okay. Then we can get the signal without the loss, okay, without the polarization loss. That is we call polarization match, okay. So if this is vertical, this should be vertical, and if this is horizontal, you will not get any power, okay. And if this is horizontal, this should be horizontal also, okay. Circular means the polarization may be changed, okay. If you are using a circular polarization with vertical or horizontal, you can get the half efficiency. Likewise, you have to match this polarization. Okay. So if you are given this polarization is matched, both are vertical or both are horizontal, likewise maybe. Okay. That means these terms you can consider as one. Okay. No polarization loss. Okay. And sometime you may be given. Actually, this is we called this PT, okay? This, wait, I can't see it, PT or PR, okay? So, give me a moment, I will check. I can't see the things in my screen, okay? Yeah, that is 40, okay? Actually, this is it is like this, okay? Okay, so this equation most probably maybe this PR P in, okay? This is the transmitted power, this is the received power, is equal to lambda 4 5 R square. R is the separation of two antenna, lambda is the wavelength, okay? Then transmitting antenna again, uh, receiving antenna again, and efficiency also may be there. PCDT, CDR. This is transmission antenna efficiency, and this is the receive antenna efficiency. Okay, and 1/4 is square. This is the transmission loss. Okay, this is the transmission antenna loss. Okay, transmission antenna loss, and 1/PR is square. Okay. This is receiving antenna loss, okay. Then you are given this polarization factor, okay. So most probably it will be 1. This is the PLF, okay. PA, PA hat, PW hat. This is we call polarization factor, okay. So it will be most probably 1, okay. But these things, these terms may become because in electromagnetism, we have learned these things, okay. Okay, so what is this? Okay, this rho T actually the transmission antenna loss, and this is receive antenna loss. Okay, so if we consider this transmitting antenna, okay, so if you send the power, okay, if you send the power in, okay, and some power will be input to this, okay, that is PT. Okay, so some factor of this PT will be propagated through this radiation resistance. Okay. And some resistance, some power will be reflected, PR. Okay. So reflected power is equal to input power minus uh, the antenna power. That is the antenna, that is the power. So this is the total power input, and some power will go to the antenna and other power will be reflected. Okay. Actually, this happens if this source impedance is not with the antenna impedance. Okay. Is not match with the antenna impedance. Okay. This is also we called as actually VSWR effect. Okay. VSWR effect also will be happen due to this problem. Okay. Actually, these things we are normally uh, um, represent using voltages. Okay, so there is input voltages and there is some voltages go inside the antenna, and there is another voltages. There is another voltage coming outside the antenna. Okay, okay. Okay, and there is something called reflection coefficients. Okay, actually, I think this is given the reflection coefficients. Okay, this is the reflection coefficients is given. Okay, so the reflection coefficients rho theta is equal to, okay, actually, that is normally referred in, rho theta is equal to, it is normally defined in voltage. Okay, so that means voltage in, okay, voltage in divided, sorry, voltage reflected divided by voltage in. This is normally referred as uh, reflection coefficients. Okay, this is the reflection coefficients. Reflection coefficients. Okay, VR divided by V in. Okay, and if you get the square of this reflection coefficients, and this also you will get the magnitude of V square. Okay, so V square means the power, normalized power. Okay, so you will have P in, sorry, P reflected, this one, P reflected divided by P in. Okay, so this you will have. Okay, okay, okay. So you can see that, okay, so you can see that the insertion loss, okay, reflected power PR is equal to P in divided by PT. Input power, okay, input power, sorry, this PT, okay, the power going inside the antenna, PT is equal to P in divided by P reflect, okay, P in divided by P reflect, okay, and if you divided all these things P in with the input power, okay, so this terms, okay, this is the transmitted power divided by P in. Actually, this is this terms, okay, this is this terms, this term is equal to this one. Okay, so now P in is equal to 1 minus P reflected divided by P in. P reflected divided by P in is rho T square. Okay, rho T square. Okay, so you can see that this term is equal to this one. The power inside the antenna divided by the power input to the antenna. Okay, so if the antenna is here, this PT is the power going through the antenna. Actually, that is radiating, and P in is the power input by the source. Okay, so PT divided by P in is here. Okay, so that is 1 minus rho T square. Rho means the reflection coefficients. Okay, reflection coefficients. Okay, so maybe you are given the reflection coefficients. Okay, reflection coefficients directly. Okay. So if we are given the reflection coefficients, you can just substitute it here, reflection coefficients. Okay. Maybe you are given the VSWR, the transmitting antenna VSWR and receiving antenna VSWR. What is VSWR? VSWR is defined as, okay, VSWR is defined as 1 minus gamma. This is the reflection coefficients, okay? Actually, that is rho t, okay? 1 minus rho t divided by 1 plus rho t, okay? Like this. Okay, so this is the VSWR. Okay, okay, okay. Then, if you are given the VSWR, you have to solve this equation and you have to find the rho t. Okay, so rho t is actually will be equal to, if you solve this, VSWR minus 1, VSWR plus 1. Okay, so if you solve this one, okay, so maybe you are given the VSWR. Then using this equation, you have to find the rho t. Okay, then you can apply it here. Okay, apply it here. Then you can find the power. Okay, then if the uh, receiving VSWR given, then you can find the rho r. Then you can find this value also. Then you can find any component here. Okay, so that is the normal procedure. Okay, so maybe VSWR may be given, or the rho t may be given directly. Okay, so maybe as I can remember, one example is there. One example is there. Okay, using phase equation. Okay, and the answer is also provided by hope. Okay, that is this one. This question, okay, this part, okay. So this kind of question will come to the exam also, okay. So you have to use this equation, okay. So you can see that here the minimum signal power is given, and you are asked to find the required minimum transmitted power, okay. So you are asked to find the P in here, okay, and the value is given 8 gigahertz. Then the antenna gains are also given in dBs, okay, and distance also given, okay. So here the polarization factor is also there, but in your question, polarization factor may be not included, okay. And the VSWR is given only the receiving antenna, okay. That means you can assume that in transmitting antenna, no VSWR, okay. That means the rho t is 0 for the transmitting antenna, okay. This part will be 0 for the transmit antenna, then will be 1, okay. So you have to only consider this part, okay. Then VSWR is given, you can find the reflection coefficients for theta, okay. Then you can find this P in value if the PR is given, PR also given, okay. So that is very easy, okay. One thing, so, okay, this DT and DR is given in decibel, okay, dB, okay. Then you have to convert this to a decibel, okay. That means you have to put 10 log 10 here and 10 log 10 here, okay. So if you put log 10, okay, so you know that if you have addition, okay, addition, if you have multiplication, so in logs those are addition, so it will be log x, log y, okay. And if it is a division, it will be a minus log. Let's say that this is a log 10 is that, okay. So you have to expand like this, okay, in the logarithmic scale, okay. So all these multiplication will become addition, then all these division will become minus, okay. So you can expand it, okay. then maybe you are asking the value from watt or dB, then you have to again convert it to the watt, okay? So that unit conversion, dB to watt and watt to dB, these things you should know, okay? So that is very simple, okay? Here you have to put 10 log 10 when you are converting watt to dB and dB watt, okay? And when you are doing otherwise, you have to get the anti-log. That is very easy, okay? Okay, so that is how you have to apply the Friis equation. I hope you can understand it, okay? So you have to focus on this equations itself, okay? Okay. Now, okay, another part, another questions also will come from array, okay? So the model questions I haven't put, okay? Model question I haven't put, okay? Actually, we have talked about array very little, okay? And maybe you can see, maybe you can remember that we have learned about the phase array, okay? We have learned about the phase array, okay? This is phase array, okay? Um, so you will get this kind of questions, okay? So here you can see that 4 elements are there and you need to focus your signal with respect to theta angle, okay? With respect to theta angle, okay? So I told you there is a, it's called, there is animation in Wikipedia, okay? So this angle happen if we delay the signal when we are feeding the signal, and if we introduce a delay to each element, okay, so we can get that get this direction, okay? So the signal will be focused into this direction, okay, if we are applying some delays, okay? Okay, so there are many techniques to apply delays, okay, uh, for the phase array antenna, okay. The one technique is using this the length of the cable, feeding cable, transmission line, okay. So when you are changing the length of the feeding lines, um, uh, the phase of the input current will be changed, okay. So that that phase, that uh, change in phase will focus the signal into a specific direction, okay. So that is one method, okay. And there are some phase shifters also you can use, okay. Phase shifters are there, okay. In our lab also some phase shifters are there, so you can use this those phase shifters uh, for the um, to give to do this delay, okay, to change the phases of this each element. These are the elements, okay, these are the elements, antenna elements, okay. And you have to feed uh, with different delays. Different delay means different phase, okay. So one way to make this delay, okay, one way to create this delay by using this kind of different length cable, okay, different length cable, okay. So if this theta in this direction, this should be uh, this should be first feed and this should be secondly feed, so on, okay. So this should be final feed, okay. So L1 should be greater than L2, should be greater than L3, like this, okay. And uh, using this equation, okay, using this equation, this theta is the angle, okay. This theta is the angle. This D is the separation of this element, okay. And V is the velocity inside the cable, okay. So the inside the transmission line, you have to find the velocity. Maybe you can remember that inside the for the transmission line, the velocity is equal to the velocity of light divided by epsilon effective. Okay, we have learned these things. Epsilon effective, then you can find the V value here. Okay, and C is the velocity of the light. Okay, so if epsilon effective is given for the transmission line, you can find you can use this equation to find the length variation. Okay, so the length variation you can find. Okay, so if you are asked to design this kind of array, okay, so you have to calculate this length variation depending on the theta given and the distance, okay, with respect to the effective transmission, effective epsilon. Okay, this is the effective dielectric constant. Okay, so I think using this equation, okay, actually you have to use this equation to do that question. Okay, so focus on this equation. Okay, try to understand this. Okay, so most probably you will be given a specific theta, and the different maybe the D also will be given. Okay, so you will be given this voltage, the transmission voltage of epsilon effective. Okay, then you can calculate this V, or maybe it is given, then you know this C, then you can find the length section, the change of lengths of the cables you have to use. Okay, so that is what you have to ask. Okay, so when we are feeding that kind of if we have that kind of arrangement, we have to use this kind of component. Actually, these are power splitters. Okay, these are power splitters. There are many types of power splitters. Okay, so once you insert the power, okay, so that power will be divided by 2. Okay, so using this kind of power splitters, you can input this the same power but with different delay to each element, these elements. Okay, these are the elements. Okay, so the power splitters are also very important when if this kind of arrangement, for this kind of arrangement. Okay, remember that one. Okay, and when we are using the power splitters, you have to match the input impedance. Okay, so the input impedance matching is done by the half wave transformers, sorry, quarter wave transformer. We have talked about QWT in matching section. Okay, so try to remember that one also, quarter wave transformer. One some example also we have done. Okay, so I think that is what you need to know. Okay, so if you know this, if you so you have to use only this equation to find the cable length. Okay, so cable length difference, actually, not the cable length, the length difference you need to find. Okay, so that is actually practical. In practically we are not using this one. Okay, but that is a simple method. Okay, this one also you can use using the different cable lengths. Okay, but practically we are normally using some electronic device. Okay, like phase shifters. Okay, and maybe some control circuits or something. Okay, so we can do this delay. Okay, okay, so I think that is enough. Okay, so what you need to do is I will upload this lecture. Okay, so if I again quickly give you a recap. Okay, so you should know the matching techniques. The notes is there. Okay, so please refer the matching, and there are maybe 1.5 questions will come from matching. Okay, and one question come from this radiation field. Okay, So most probably you will be given a radiation intensity. Then you will ask to find the directivity, half power beamwidth, so on like that. Okay. So, so maybe the half power beamwidth also maybe you have to find. Okay. So I think maybe you can remember we have done some example. Okay. For the half power beamwidth. Okay. So if you know the U, okay, theta, you can find the half power beamwidth. For example, let's say that U theta phi is given as a cos theta or something. Okay. Then let's say that this theta is from 90, sorry, theta is yeah, less than between 0 and 90, and it is 0 between, let's say that 90 and 180. Okay. So if you are given this kind of radiation intensity, if you are asked to find the half power beamwidth, what you have to do, you have to first draw this intensity. Okay. So you have to use the xz coordinate. Okay. And this will be x. Okay. So x will not be used. Okay. So theta is given. Okay. Most probably theta will be given. Okay. So you have to draw this in zy plane. Okay. Because theta is in zy plane. Okay. And phi is in xy plane. Okay. So if the phi is given, you have, it will be a 3D uh, pattern, 3D pattern, 3D intensity pattern. Okay. So most probably you will given a one uh, one uh, dimension, one plane. Okay, here it is ZY plane because you are given theta. Theta is in ZY plane. Okay, so um, so uh, so when the theta is 90, okay, sorry, when theta is 0, okay, when theta is 0, uh, the radiation intensity will get it maximum value A. Okay. When the theta is 90, okay. When theta is 90, it will be maximum. When the theta is 0, sorry, when the theta is 90, it will be 0. Okay. When the theta is 0, it will be 90. Okay. So if you get, it will be maximum. Okay. When the theta is 0, it will be maximum, and 90, it will be 0. Okay. And if you consider the half point, let's say that 45, at 45, okay. So you will have some value like this. And here also you will have some value. Okay. So your intensity will like this. Okay. And if it is symmetrical, you will get this kind of one. Okay. And you have to get the half power beamwidth. That means that you have to select the half power point. Then you have to uh, find this angle. Okay. So if this angle, this one angle is alpha, okay, one angle is alpha. So A cos alpha should be equal to the half power. Okay. Half power means half of maximum. Okay. So maximum power is A, that should be divided by 2. That will be the half power. Okay. So A cancel out. Alpha will be cos inverse 1 over 2. Okay. Maybe this is 45. I hope. Okay. I'm not sure. Okay. Just check. Okay. Then alpha will be, so the beam width, half power beam width will be 2 alpha. Okay. So that is how you have to find the half power beam width. Okay. So that kind of questions also will come. Okay. So anyway, if you are given this kind of things, intensity power, you can find the half power beam width, and maybe you are asked to find the directivity function or directivity. Okay. If you are asked to directivity, you have to find the maximum. Here the U max is A. Okay. U max is A. Okay. Then the directivity is A divided by 4, 5. Sorry, A divided by T 4, 5. Okay. This is the directivity. Okay. So you have to find this PT. Okay. So to find the PT, maybe you have to do that integration U theta 5 with respect to sine theta d theta d 5. Okay. And this limit should be 5 limits, theta limits and 5 limits. You have to verify it. You have to do this integration, or maybe Pt you can find by applying this equation, I square r radiation. Okay, so both the techniques you can use to find the total radiated power, then you can find the directivity. Okay, so that is you need to know. Okay, then you need to know how to use the Pires equation. Okay, one example is there, two examples is there, so try to do the two examples. Okay, then you need to uh, find the length of the cable, the length difference of the cable. If the phase array is to be is going if we are going to design a phase array with different length transmission line. Okay, so that is what you have to do. The exam question will mainly depend on these things. Okay. Uh, okay, so I will upload this recorded session. Okay. Mm, as soon as possible I can. Okay, so then